That doesn't sound good. Doesn't
Uh,
sound.
It does not sound good?
no, I don't hear you, Daryl. We don't hear you.
You should be able to hear me.
A little bit.
So about 3 dB above
Loud on
above
this end.
zero.
Yeah.
Oh, he's down about 9 dB. He's faint.
Yeah, David, what you were talking about absolute zero is beginning to look at that. Zero sound.
No sound. There's no sound.
Goose egg.
Yeah. We had it for a moment.
That mic's muted. I'll bet you.
Yep. Yeah, because he had some sound to start with. He
Yes,
just
he
needed to
did.
turn
Yeah,
up
but
the
it was very
volume.
faint. Yeah.
Yeah, there wasn't very much.
Yeah, Evan, check the mic.
We're checking on the
mic is
sound.
on.
So the more you talk, the louder it is
Mic
in the
on.
theater.
We don't know why they're not hearing it
Oh.
on Zoom yet. Hey, here comes my ticket. Is this the winning one?
Nope, big fat goose egg.
Nothing.
There's another mic that's picking him up, but not that one, not the main one.
Or does he have it turned on?
That's the question.
Right
on
under
Zoom
his
yet?
hand towards the end of it is a little switch that goes side to side.
It is unmuted. We're testing it. We're getting the audio in the system so far. Hold on, give me a second.
Well, we got an okay showing here. You guys all make it through the traffic okay?
Yeah, there he goes.
There.
So faint.
It was not easy, and I came early.
Unbelievably soft.
Yeah.
Mm-hmm. Mm-hmm.
I can speak up, but it's really loud on this end.
Wow.
Okay.
Can you hear
that's
me at
a-
all?
This is weird.
We can understand what you were saying, though.
Okay.
That's good.
All right. So
That's
a
better.
couple of things. One is there's a letter that went out today about bylaws and conduct update. We have to change some of the wording, and that does have to go to the general membership for a vote next month. So you'll see in Groups IO, Alicia sent out a letter that says LAS board and officers put together bylaws, elections, and code conduct update committee to add changes and some grammatical updates to the current bylaws, the election process, and code of conduct. Please review the following changes over the next 30 days. The membership will vote on the changes at the next general meeting in October. Please send any questions or inquiries to Secretary or Alicia. Email addresses are in the letter. So that went out today. Andy sent that out to the general membership. So take a look at that. The attachment is the revisions to the bylaws. It's in a PDF format, so you should be able to open it and read it. And then we'll vote on that next month. Okay. Some updates and announcements real quick. At Garvey, we have some new security cameras, and the Starlink is up and running. And Halloween Science Night, big night there, is going to be Saturday, October 26th. So come and bring your costume. Bring your dog with his costume. Bring your cat with his costume. Yes? What time? I believe it starts at, in the afternoon. Is it in the afternoon that we start that? Starts at 2 or 3 until the park closes, which is probably around 10 o'clock. And there's a lot going on there. We have a whole bunch of presenters, and people get set on fire, and we set off rockets, and all kinds of things happen. Many giveaways, lots of candy and prizes. Are we going to do hamburgers again this year? Okay, so we're going to be doing food as well. Joe and Zolly will be there. Yay! Okay, really good. Let's see. At Lockwood, we have mitigated all of the violations that we had at Lockwood, and finally, we got there. The shed is gone. We have a new roll-off observatory, and we are able to move forward to get electrical permits to get that electrified. We've been doing a lot of tests on it. It's going to work really well. It's going to be a completely automated roll-off observatory system. You'll be able to go to a website, put in requests for objects to be photographed. They will be photographed, and the contents will be uploaded to, I think it's a Google Drive, and then you can get all of your data and process it to your heart's content. There's going to be 2 observatories up there. One is going to be completely automated. The other one will be for visual. And I think we just got a 16-inch telescope set up that we're going to use in the other roll-off. Some bad news is the bridge fire took out Ford Observatory completely. It's a total loss.
Oh, gee. That's too bad.
We were probably going to have to do some cleanup up there. And after that, unknown. It's not something that we can rebuild. It would have to be something that would be a complete new building. The building there is completely destroyed. All I can see from the cams that we can see is the dome pretty much lying on the ground.
Daryl?
Yes, sir.
Me. It's Curtis Ford.
Yes, Curtis.
Ford Observatory. It appears as though the dome is sitting on top of the telescope. The top cage of the telescope was broken off by the dome when it fell. Greg Thomas was able to get up there on Friday, and I've got a series of about 30 pictures that he sent us. As soon as we can get an opportunity to go in there, we will make an assessment. And we're kind of hoping that the mirror may have survived, but we don't know. So we just have to wait till we get up there to see what but overall, it's pretty bad, but the mirror may have survived. We don't know until we get up there and check it out. But
Okay.
yes, we're going to have to get a crew out there. Probably going to have a professional crew out there to clean up the mess. We got to have a crane out there to pull the dome off. But prospects of rebuilding, we don't know. We don't think so at this time, but you never know with the forestry. But if the mirror has been damaged to a point where we can't use it, it's worthless to do anything up there.
Okay.
So until we get up there to do it, then to inspect it, then we won't know what's going on.
All right. It's all bad news, though, so far.
Yes, bad news.
Okay. Also, in December, we have nominations and elections coming up, so keep that in mind. Part of the new bylaws have to do with that. I'm not going to read these. There's the summary of the major changes. There's not too many, but nominations, let me tell you about just the nominations. The general membership and the board encourage people to submit nominations. Then the nominees must accept the nominations. You can't just nominate somebody and have them and just get hijacked onto the board. Can't do that. The nominations must be received and acknowledged by the secretary before the ballots are distributed. We did a couple of updates on just other wording, and you can read all of those in the overview of the revisions, and that's on the PDF that got sent out by Andy today. Let's see, what else do we have? The only other thing I have is there's the last Mount Wilson date is October 4th. It's a 100-inch night, and it is completely full right now. Unless there's any cancellations, we'll be having a good night, I hope, weather permitting. Let's see, I don't think I have anything else. Well, that brings us up to our guest speaker then. Oh, is there any new members in the house? Any brand new members? Are you? Sure, hold on, let me give you the mic. Hold on a second.
Next star party will be the 12th here. Carol?
Go ahead and introduce yourself.
Hello, everyone. I'm Norm Thoren from Redondo Beach and part of a small group in that area that gets together every now and then.
We're a bigger group than this, but
I know you're a lot bigger.
you could have met in the conference room.
Thank you for coming tonight and making it through the traffic. What was the other announcement that I missed? The next star party?
It's going to be Saturday, October 12th.
Saturday, October 12th?
We're only here, we're here from 2 to 9:30. That's it.
Okay, so from 2 o'clock in the afternoon until 9:30, come and look at the sun in the afternoon and whatever we got to look at after dark.
And we also have family night at Lockwood on the 28th.
Okay, family night on the 28th at Lockwood. That would be the last one this year then?
That's correct.
Okay. September 28th.
Mm-hmm.
Okay. All right, well, that brings us up to our guest speaker tonight, which is our own Tim Thompson. He's going to be speaking to us about the moon, including its origin, why our side looks different from the other far side, its orbit, what people observe, and a host of other topics, including supermoons and micromoons, which I don't think I ever heard of before. So I will introduce Tim Thompson.
Yet, okay. Oh, good. They're back in the shop diddling the microphones while we stand out here in the back room where they're all hot and sweaty with the electronics. They're going, quick, move the things up, move the things down, make the microphones work. So hopefully everybody can hear me okay. There's the things on the screen. So I'm here to talk to you about the moon. And I just thought for my introductory slide I'd show an image of the moon made by the Galileo spacecraft. Because if you remember, it was heading for Jupiter, but of course they had to go to Venus first and the Earth twice before they could get to Jupiter. And I don't know how those people at JPL who figure out trajectories work, but if I was sitting there thinking, I've got to go to Jupiter, let's see, why don't I go to Venus first? Would not be the first thing I would think of, but that's what, and it worked, you know. And you can see from this image that the moon is much darker than the Earth. The moon's in the foreground, moving to the right. And so we're going to talk about all that and the moon, etc. So here are 4 images rotated 90 degrees from the Lunar Reconnaissance Orbiter camera. The near side, the side we can see from the Earth, is on the upper left. Rotate it to the left 90 degrees and you get the east side, as you can see. Rotate that 90 degrees, you get the far side, which is on the lower left. Rotate that 90 degrees, you get the west side. So you're looking at the whole moon. And of course, the one thing you see right away, now that we know what the back side, not the dark side, of the moon looks like, it's obviously much different than the front side, and everybody wants to know why is it different, and we all stand around and go, well, it's kind of, somebody said something, and yeah, nobody knows. So let's see, there it is, there's my trusty cursor. So you see all these big dark C's here on the side that faces us, and there's like not much going on that way. However, if you look down at the bottom of the far side image, there's a big dark thing, which of course people didn't really see until we went over and looked at the dark side of the moon, the far side of the moon. And that is the South Pole Aitken Basin, and it is an impact structure, roughly 1,600 miles across and 4 to 5 miles deep. So that is a serious crater that was caused very early on in the history of the moon. And if we take a look at the mineralogy of the moon, diametrically opposite the Aitken Basin is where the big C's are. That's called the Procellarum creep terrain. Creep doesn't mean it's weird. Creep means potassium, rare earth elements, and phosphorus, which has a much lower melting point than the rest of the moon. And as you can see, there's also an anomalously high amount of thorium in the Aitken Basin, which probably confirms that it is an impact nature. So it appears that the impact that hit the South Pole Aitken Basin actually pushed a bunch of stuff through the moon. And here's a couple of papers The one in 2020 is doing some heat experiments to prove that in fact the melting point is much lower. The guys in 2022 on the right are studying the impact and how does the moon evolve after the impact, and convection currents carry the creep terrain across the moon. And the result is that you can have a lot more magma under the crust on the near side than on the far side. So if you punch a hole in the crust, you get a lot more magma coming out. Hence, you get the big C's on our side and not on the other side because you don't have as much magma under the crust. That's the going explanation. So remember that the next time at a star party when somebody asks you, well, it's creep terrain and it's the depressed melting point, and I got my degree in geology from MIT or whatever. So that is the most likely reason why our side looks different than the other side. The next obvious question is, where did the moon come from? If you go back in time, there are lots of theories before anybody knew what they were talking about. They thought maybe the early Earth was spinning real fast and the Pacific Ocean basin is what's left over when it flung off the moon. We know that doesn't work today, because they didn't know about plate tectonics back then. There are a lot of problems with the moon, Earth-Moon system, one being it has way too much angular momentum in it, and the other being that the moon looks to be made out of almost exactly the same stuff as the Earth's mantle. You might be able to do that if the Earth and moon form together, but it's easier if you do an impact. So what I'm going to do is play a movie here that is the highest resolution impact. There we go. Highest resolution. I turned off my sound and you're not supposed to hear that. Not supposed to hear the cheap NASA music, but squeeze and elongate because of the tidal forces. Bad day on Earth for anybody there, as you can tell. What's that?
You got the music off for you.
Yeah, thanks. I thought I silenced my computer. In the absence of cheap NASA music, let me try playing that again, and you can see that the model runs a couple of times. It almost blows the Earth apart. So it requires a relatively low velocity grazing impact to create the moon like this, and that is an unusual thing. So in order to arrange it, Theia couldn't just be some Mars-sized thing floating around. It had to be at the Lagrange point, get perturbed out by solar gravity, and then move to give us this relatively low velocity grazing impact as it kind of spirals in towards the Earth. So this model is the highest resolution in space and time and shows details like the two blobs forming, like Helmholtz instabilities in all the junk that's blown out. The outer one becomes the moon because the inner one gives it a gravitational assist, flings it out into an outer orbit. So this model solves a number of problems. One is that the Earth is way too hot inside. nobody can explain why the Earth isn't frozen solid inside. It's a geophysical mystery. This rejuvenates the Earth, reheats it, resets the clock, solves that problem. There's way too much angular momentum. You can't possibly have captured the moon with the kind of velocity and orbit it has. Can't happen. This solves that problem by combining the angular momentum of Theia and the Earth. And it solves the problem of the chemical composition of the moon matching the mantle of the Earth. So naturally, last month, a paper came out with some geochemists arguing that the crystal structure in the moon can't be created by an impact, and I don't want to hear it, because if you go that way, then you have all these other problems you have to solve again that you just solved this way, right? So this is the obvious solution to the problem. But aside from solving the problem of the Earth-Moon system, it curiously solves another problem you might not have thought of. And that is that down deep inside the Earth's mantle, and it's been known since the 1980s, maybe the 1970s, there are these large low-velocity provinces. Low velocity means low seismic wave velocity, so their density is less than the rest of the mantle, and they're different from the rest of the mantle. And people have had a hard time figuring out what's going on. Well, a paper published late last year, the authors have been modeling the evolution of the Earth-Moon system after the collision and have decided these are bits and pieces of Theia, the Mars-sized impactor that created the moon, that are now buried at the bottom of Earth's mantle. And that explains how these weird things got there. Aliens, right? They came from somewhere else. So, and so we solved not only the Earth-Moon problem, but we solved the geophysics problem too. So now that we've got through solving all of our problems, let's just look at the moon for a minute. It's big compared to the Earth, nearly a quarter the size of the Earth. It's the only moon other than Charon, the moon of Pluto, in the solar system that is that big compared to its planet. And that's one of the reasons for saying there's too much angular momentum, it's got too much mass, there's too much going on. And so it's big enough, you could lay it on top of the United States, something like that. So it's big compared to the Earth. And it's also big compared to other moons in the solar system. And so I put a count up here above each planet. I checked the JPL small body database today before coming here and put on here up at the top how many moons. You'll notice that Saturn has graduated to 146 moons and Jupiter only a mere 95. And if you've been looking at Saturn lately, you know the rings are almost edge on. When the rings turn edge on, that's when the satellite hunters go out there because the rings aren't in the way anymore and go looking for new satellites. So who knows, maybe after this ring plane crossing, there'll be 180 satellites for Saturn, and we'll see. But the moon, our moon, is the 5th largest satellite in the solar system. Ganymede, Titan, Callisto, and Io are larger. Io just by a smidge, like a couple of 100 kilometers in diameter. It's almost the same size as the moon. And things like Triton, are much smaller. On average, and really does mean on average, the moon is about 30 Earth diameters from the Earth. So you could line up all the planets, and so this image shows you the Earth on the far left and the moon on the far right, and the acceptable planets lined up between them. And of course, there's plenty of room for Pluto. You can stick Pluto in there, and they still all fit between the Earth and the moon, which I thought was kind of an interesting bit of trivia. If you get somebody who's had a little too much to drink at your public star parties, how many planets can you fit between the Earth and the moon? That'll keep them busy for a while. So this is a diagram of the orbit, which makes the system look way too simple. It's not this easy. But basically, the orbit of the moon is tilted about 5 degrees up compared to the plane of the ecliptic, where the planets hang out. And the Earth's axis is tilted 23 degrees down. That's why the declination of the moon varies so much. Sometimes it's high in the sky, sometimes it's low in the sky. But you get the idea from a diagram like this, like, okay, the moon's always in the same orbit, it's doing the same thing all the time. it's not. It's highly variable. And there are a whole bunch of cycles. And I just want to talk about one for a minute, the Saros cycle. You might think that the moon going around the Earth is a fairly simple thing, but as you can see, if you time the moon from new moon to new moon, or time it from perigee to perigee, or just time it from node to node in the orbit, you get different months. So you have to be careful when you talk about a lunar month, which month do you mean? Because there's more than one. And if you add up 223 synodic months, 239 anomalistic months, and 242 diachronic months, they come to the same number. And the ancient Greeks knew this, the Babylonians knew this, and knew that eclipses repeated, solar eclipses repeated in a cycle that is defined by the Saros cycle, which is about 18.04 years. But there is an 18.6 year period that comes from variation of the inclination of the orbit of the moon in the declination, and that's what gives you the lunar standstill phenomenon, and there's standstill markers outside. If you come here, especially at lunar standstill time, you can watch the moon rise right above the little marker. Griffith Observatory is an observatory. You're supposed to come here and observe. So there's a whole bunch of different cycles. So this is generally for people who are not already astronomers. I'm sure most of you already know why the moon has phases. I once taught phases of the moon to a bunch of elementary school teachers for the Astronomical Society of the Pacific, and it was really interesting. About half of them got it right away and were done. The other half, you really had to treat them like elementary school students, have Mr. Sun stand here and Mr. Earth go around and turn this way and look that way at the flashlight, and they eventually got it. But it's surprisingly difficult for people in general to understand the phases of the moon. When it's just moon there, sun there, light there, we're done. But yeah, that's the way life works. Tonight's moon, of course, is a 98% waxing. Gibbous moon and full moon is tomorrow. That's going to become important in a few minutes. Two things about the moon like that are going to become important. And I put the blue arrow to point where's the moon in its phase diagram tonight, pretty close to full, almost full. So this is a list, and in my next slide I have a movie that's more interesting perhaps than the list. But this is the moon for 2024. I used the Formulab calculator for apogee and perigee. And you see the distance in kilometers at perigee, the distance in apogee, and you will notice that each one is at a different distance. The moon's orbit is not constant, and in fact, every time the moon goes around the Earth, it is in a slightly different orbit. The perigee is different. It'll never be the same again. It's different every time because the planets are pulling on it, the sun's pulling on it. So it's not a constant thing. So, of course, I got a call from a panicked LA Times reporter who was breaking news, wanted to report about the supermoon in August, 2 days in advance. Quick, tell me about the supermoon. Well, that's what they call a full moon near perigee because the moon looks significantly bigger. You'll see an example of that in my next slide. So naturally, I told her that actually there's a supermoon every month. They're not weird. It's just that sometimes the full moon, and that's what people look at, like there's werewolves or something. So the August, September, October, and November full moons, especially the September and October, tomorrow's, are supermoons. But supermoons get all the press, and nobody ever calls me to ask about the micromoon. It's like, nobody cares. So notice that the full moons in February and March were very close to apogee, which means they were unusually small, not unusually large, so they're micromoons. And nobody ever gives the micromoons any love or press or anything else. So you got to go out there and push. Every time somebody asks you about a supermoon, you say, what about the micromoon? Nobody's paying attention to the micromoon. Now this slide, I'm going to run a movie. NASA posts this. I have the URL there at the bottom of the slide. They post these around Christmas time, late December every year. Just change the 2024 to 2025 and it will take you to the 2025 one if they upload it. If you look in the upper left corner, this dot, when I run the movie, you'll see this little moon dot running around the circle. When it's out near the edge, it's at apogee, and inside it's near perigee, and you'll see the image of the moon grow and shrink as it gets bigger and farther. This shows you the orientation of the moon. All the numbers are here. It's the whole year in 1 hour steps. And so I'll just go ahead and run that. So you can see not only is the moon getting bigger this time at new moon, but the February and March full moons would be super moons. But you can see the image of the moon getting bigger and getting smaller as it moves towards apogee, and you can see that on the little clockwork diagram in the upper left. You'll also notice that the moon is wobbling considerably. It's not just keeping one face towards the Earth as you might have thought. Part of that wobble is libration. The moon actually is not tidally locked to the Earth yet. It's working on it, so it swings back and forth. From the Earth we can see about 60% of the moon, a bit better than half. And also, because the orbit is so highly tilted, if you're looking at the moon from the north or you're looking at the moon from the south, you're going to be able to see a little more on the north side or a little more on the south side. So your viewing geometry is going to change things too. So this whole thing runs for about 5 minutes. I'm not going to run it all the way through. You can download it yourself from the URL that I put there at the bottom of the slide and sit there and stare at it all you like. But you see that the motion of the moon is more complex than you would naturally think. So in every amateur astronomy club there are lunatics who spend their time looking at the moon. We had a guy last year who rented a night on the 60-inch telescope and looked at nothing but the moon all night long. And he had a long list of times when the sun would shine right down this valley or right between these mountains, or it would light up this peak. He had them all figured out. He knew what was going on. So it was easy for the telescope operator. All he had to do was move the telescope a little bit. So what do people look at? Here I have an example. I thought I moved further. Okay, here we go. Here I have an example of two images of the crater Copernicus. The one on the left is made by a very expensive spacecraft orbiting the moon, and the one on the right was made by the guy whose name I'm not going to try to pronounce because I'm sure I will butcher it completely, with a C-14, which is a telescope similar to one many of you have. And as you can see, it's pretty good competition for the Lunar Reconnaissance Ranger. What do we need the satellite for? We can get a bunch of amateur astronomers and do that from here. The light, of course, on the left-hand NASA image is coming in from the left. The light from the C-14 images is coming in from the right. And it's a great optical illusion. If you convince yourself that on the left image the light is coming from the right instead of from the left, you suddenly see a hill instead of a crater. I can see either one at will. I can see a crater or a hill. So you should be able to convince yourself that you're seeing either one. But another thing about this is the changing of the light changes what you can see. So you can see there are features up here in the upper half of the crater that show up fairly well when the light is coming from this way, but don't show up as well when the light is coming from this way. You can still see them, but they change considerably because of the difference in lighting. So the real moon observers will go out at very particular times when there's a peak lit up they want to look at, or maybe they want to see the crater from this side or that side. Here's another feature. The correct name is Rupus recta, but we call it the straight wall. The image on the left, this image is what you normally see. Most of the pictures show the Great Wall in shadow. That's because the light is coming from the left, so this side of the crater is in shadow. But here's a picture that shows the light coming from the left and lights up the cliff. And I notice in this image you can see the folds in the ground here because they're lit up on this side. But if you go looking for those over here, yeah, you can sort of see that they're there, but they really just don't stand out at all the way they do in this image. And of course, this side is much more detailed than this. So the lighting is a big deal. So for moon observers, they can be very picky about when they look at something. Now, you all know about the Messier marathons, where in one night you look for all the Messier objects. How about in 1 month you do a lunar alphabet marathon, because there has to be a lot more alphabet letters on the moon than just X, Y, and L, or V. There's got to be a Z, there's got to be a Y, there's got to be a Q. You moon observers need to study the moon and find the alphabet, and then we can have a moon alphabet marathon that lasts for a month, okay? And so these things, like the lunar X is probably the most popular, these are ephemeral. They only last for a few hours because they're caused by sunlight streaming between craters, between mountain peaks, lighting up the little sides here. So you need to be well-timed to go and see. You need to know when, and you can predict that in advance. You need to know when it's going to show up to go and look at it. So for just observers who want to set up a telescope and look at something, the moon has a lot of interesting stuff on it for you to look at. Now, I can't spend the whole talk all night talking about what you look at on the moon. Moon observers in the club already know that. But, you know, set up and look at the moon a little more carefully at the next upcoming star party. See how that works. Now, contrary to some hot rumors on the internet, we actually have sent people to the moon. I remember it. The Apollo 11 in 1969, and we finished up with Apollo 17 in 1972. We're going to send people back to the moon, or so they say. Of course, nobody went to the moon to do science. They went to beat the Russians, and once the Russians weren't going to the moon anymore, they quit. Which always bothered me, but that's my problem. Now here, we have lunar reconnaissance orbiter images of the Apollo 11 and Apollo 17 landing sites, and you can see boot tracks and rover tracks and the instruments left behind in the landers. There are three things interesting about this to me. First up on the upper right, you see the Apollo capsule. A few years back, actually several years back now, I tutored a 13-year-old girl in Beverly Hills with parents who were too rich because they paid me way too much money to tutor their daughter, but hey, I'll take it. She was going to do a school project on the Apollo missions to the moon. So I talked to her for a few minutes and quickly realized she thought that the astronauts went to the moon in the space shuttle. She had no idea that there was an Apollo capsule. They'd never seen it, didn't know anything about it. So I had to teach her that 3 guys crammed into that little tin can and went to the moon, and she was quite shocked to learn what ancient technology looked like. So remember, you know, the kids these days, you know, every generation says that, you know, so I'm going to do it too. In the center picture, the little red dot up here on top, that's what you're trying to get into space, and maybe part of this because you need to get the lunar excursion module up there with it. You're just trying to get this little thing up into space. Why do you need this enormous rocket to do that? Well, you can figure out how much energy you need to get up into space, get up to the moon, and then you can build a gas tank, fill up the gas tank, light it off, it'll take off, it'll go up, and then it'll come back down. Because, of course, you like doubled or tripled the weight at launch with all that fuel. So now you don't have enough energy to lift it. You need more fuel to lift that extra fuel, but if you do that, it still won't go anywhere because the new fuel you lifted to lift the old fuel also weighs something, and you need new fuel to lift the new fuel to lift the old fuel, and so there's a cascading effect of you need the fuel that lifts the fuel that lifts the fuel that lifts until you finally wind up with that great big thing, so all you're lifting is the fuel. If we had some other way to get off the Earth, we could save a lot of gas. But that's why you want to build things on the moon, maybe, and take off from the moon without taking off from the Earth at all. But the real fun story is the guy on the left. That's Neil Armstrong taking the first step onto the moon. So the way this was done was a television camera on one of those things that looks like an old ironing board that flops out of the wall. It flops down. There's a television camera on it pointing at Neil, pointing at the ladder, watching him walk down. That television signal was sent to the Earth and displayed at the control station, at the receiving station, on a television screen. That television screen had a television camera looking at it that then recorded the television screen and sent that signal to the world. So that's what we see. That's what all this is. The original signal was recorded on magnetic tape. But this was 1969, and magnetic tapes are expensive, and you reuse them. And so the Apollo 11 tapes were not properly marked, and they were erased in a routine tape recycling ceremony. And therefore, the original signals are entirely gone. And the only data signals we have are the signals that came from the television camera looking at the television screen. So if we had the original signal, we could digitally enhance it, clean it up, and do that kind of stuff. So maybe that's good, maybe that's bad, but it reminds you that technology in 1969 was quite primitive by today's standards. But there are many of us in this room who remember 1969 fairly well and probably used the technology of 1969 and at the time thought, wow, this is really cool that I can do this. And now you look back on your childhood and think, wow, that was really crazy, wasn't it? So that's why we have no better images of people, of Armstrong landing on the moon, because it was erased. We are indeed going back to the moon, or so they say. There was an Artemis 1 test flight back in 2022 that just kind of went up. I think it went around the moon, actually, with nobody in it. The Artemis 2 mission will go up no earlier than next September, and that will take 4 astronauts into orbit around the moon. And then in 2026, they will actually land on the moon. They'll need another lunar excursion module. You can see in the upper left there is the Orion space capsule. It's about 1.5 times bigger inside than the Apollo capsule was. Not a whole lot bigger, but a little bit bigger. It'll hold 4 people instead of 3, and they actually have enough room to get out of their chairs and kind of walk around like this. or something like that. I mean, there's a little room in there. But all these dates are no earlier than dates. And so who knows when they will actually launch, and they've got like 6 missions on the calendar. Who knows if that will happen. But of course, we're only going to the moon this time to beat the Chinese, who are going to the moon. But maybe they've learned their lesson. Somebody's always going to want to go to the moon. Maybe we just go there and we'll be there already when they get there, and then we can claim the place for our own or whatever. So if we go back and take a look at Apollo 11, you notice LRRR is one of the instruments left behind. That's a laser ranging retro reflector. And here's a picture on the lower right of the LRRR left behind by Apollo 15. And on the left is a telescope collimated laser beam that is fired at the moon looking for one of those reflectors from Apache Point Observatory in New Mexico. You can see the laser beam has the aperture of the telescope. This is probably a few meters. I don't know exactly how big their telescope is, but it's a fairly well collimated beam. When it gets to the moon, that beam is, I think, 4 miles across. And out of every 100,000 trillion photons of light we send to the moon, 1 makes it back. But that's enough. We can count that photon and use that retroreflector to determine that the moon is moving away from the Earth at about 3.82 centimeters per year. That's almost exactly 1.5 inches. And you might think, well, wait a minute, gravity pulls, it doesn't push. So how can the moon be going that way when the Earth's gravity pulls it this way? And that's another one of those complications in the Earth-Moon dynamical system. If the Earth were not spinning, the high tide bulge would be pointed straight at the moon. But it is spinning, so the moon pulls this part of the Earth towards the moon, pulls the oceans towards the moon, pulls the Earth away from these oceans. That's the standard explanation. But because the Earth is spinning, it spins and pulls this high tide bulge away from the moon. A better explanation is that the moon, because it's not a point source, is actually squishing the Earth like this. And when you squish anything, right, it squeezes out. And that's what's really happening. Either way, you get the high tide bulge at an angle. And so because the Earth is spinning, it's like attaching a cable from the Earth to the moon, and you whip it. And so the Earth is whipping the moon forward in its orbit, transferring momentum from the Earth to the moon. So the spin of the Earth as a result of this is slowing down by about 2 milliseconds per day per century. So in 100 years from today, the Earth will be spinning on its axis 2 milliseconds slower per day than it is now. And of course, if you have a really good stopwatch, you might notice that, but probably not. So it's going to take the moon about 25 billion years to get out to a point where the moon is no longer librating. It really is locked to the Earth. And the Earth is really locked to the moon, which means people on the back side of the Earth will never see the moon because it's only visible from one side of the Earth. And then you'll have all kinds of great conspiracy theories about, well, there is no moon. I've never seen a moon, but you have to go to the other side of the world. Ah, it's a prank. It's a NASA trick, whatever. And then at that point, the sun pulling on the moon will cause it to come back to Earth. And about 25 billion years after that, about 50 billion years from now, we would expect the moon to catastrophically rejoin the Earth. Having left it, in the great collision that you saw earlier, it'll come back. However, the sun will destroy the Earth completely, most likely in about 5 billion years or less, so that probably will never happen. And I'll point out that Phobos, the larger moon of Mars, and I believe Triton, the moon of Neptune, are both on their way back towards their planet now. Phobos will rejoin Mars in about 60 million years, a fairly short time astronomically speaking. Triton will be a lot longer. Triton's big and it's a lot farther out from Neptune. It'll take a lot longer to rejoin Neptune. But Phobos will rejoin Mars in only about 60 million years or so. Now, eclipses, of course, are something that we're all familiar with now, especially after last April. Then sometimes the moon gets in the way of the sun from the point of view of the Earth. I emphasize that the diagram is not to scale. Astronomers already know that, but non-astronomers, you kind of wonder about them sometimes. The sun is not really that close to the Earth and not really the same size as the Earth, but you can see the shadow geometry laid out there. The penumbral shadow where you see a partial eclipse and the umbral shadow. A better example is something that you've probably seen before. I suspect that I've done it before, is this movie, which shows you the moon spinning around the Earth. The Earth has a big, long shadow. Remember that. The moon is much smaller and has a skinny shadow. And every once in a while, the shadow hits the Earth. Most of the time, because of the inclination of the moon's orbit, its shadow just misses the Earth altogether. We don't see an eclipse. But every once in a while, kaboom, you get in just the right spot where the tiny little point of the shadow actually touches the Earth, and you get a total solar eclipse, because the moon's shadow is much, much skinnier than the Earth's shadow. And this is the result. So here you have to be, this is last April's eclipse, you have to be on the yellow path in that little black circle. And Evan and I were in Kerrville, Texas. We were right about there and got clouded out and didn't see anything. But you can see it's kind of a complicated path that the totality follows. Over in the lower left is the duration of totality in minutes and seconds, and we were pretty close to maximum where we were in Kerrville. The period of totality gets longer and then it gets shorter. The moon sometimes closer, sometimes farther as it moves along its path. The Earth is spinning, the moon is moving. Everybody in that big outer circle saw a partial eclipse. So the whole 50 United States, the panhandle of Alaska and all the rest of the states, saw at least a partial eclipse. Now, not all eclipses, of course, follow the same track. So just to get the geometry across, here is a slide that shows you the eclipse tracks from 2021 to 2030. The orange paths, these paths here, are annular eclipses, and the yellow paths are total eclipses. I think there are 6 of each, as I remember my count. And there's one hybrid eclipse that's partially total and partially annular, because the moon is right there on that sweet spot where it's exactly the same size as the sun. So if you tweak it a little bit, you get an annular. Comes a little closer, okay, and you get a total. They're a little on the rare side. There's only one here. But as you can see, they're all over the place. And I know several people listening to me are eclipse chasers and will go chase every eclipse. Most of the time they're out here over the ocean, like the 2020 eclipse. In 2028, there will be an eclipse through the middle of Australia. In 2026, there's one that touches northern Spain. There's an annular eclipse in 2030 if you want to go to Siberia. Not on my favorite list of places to go, but the people who chase every single eclipse there is, they'll go there. They'll go wherever. So who cares about eclipses? Well, there's a bunch of reasons to care about eclipses, and one of them is historical. This is a Babylonian solar eclipse tablet. This one lists eclipses between 518 and 465 BC. It's from the British Museum. Now, it's not old enough to talk about this particular eclipse. This is the Assyrian eclipse of 15 June 763 BC. So ancient calendars are all reference to some event in their lifetimes or in their society, the coronation of a king, the burning down of the town, whatever. And so you know the dates relative to this big event. But you don't know when that big event happened, so you don't know what to do with that little strip of calendar you have. Where do I put it in our calendars? Over here, over there? But if they see an eclipse, they write it down. Everybody wrote down every eclipse they saw, because when the sun blinks out, that worries you, right? Of course, the ancient Greeks knew what they were looking at. It was the moon, but they kept track of all this. So sure enough, there was one in 763 BC. At this town, at this place, at this time, the sun winked out. We can run the eclipse machinery backwards and figure out, okay, it was this town, it was this time, it was this place. It must have been this eclipse. And now we can pin that piece of ancient calendar to our own calendar as an absolute date rather than a bunch of relative dates. And if you do that with as many ancient calendars as you can, now you can compare the ancient calendars to each other, which you can't necessarily do because they're all relative to something they're used to. And if you want to connect the Assyrian calendars with the Egyptian calendars, you may go, I don't know, which was first, which was next. If there's an eclipse in there, now you know. And if you're trying to correlate events in ancient history, that's a way to do it. Correlate their calendars to today's calendar. Now you know what caused what and what didn't. So ancient historians are big on eclipses. Another reason for being interested in eclipses is proving general relativity is right. So this is a photo plate made by Arthur Eddington, who went out to, I think it was Principe. It was an island off of Africa, where he photographed the sun in the Hyades open cluster, and he had a photograph without the sun. And by looking at the difference in positions of the stars, he said, well, okay, their difference changed, the position changed by an amount predicted by Albert Einstein, and thus proving general relativity. And then fairly recently, a bunch of scholars studying his data decided, okay, his data probably aren't really good enough to do what he says he did with them. And then another book came out a couple of years ago saying, yes, his data were good enough. Yes, he could prove general relativity is right, but it's gone down in history as general relativity being proved right anyway. And another reason for being interested in eclipses is because they're cool. And here's a cool photograph made by David Pinsky, who is sitting right down here at the front of the audience in the 2017 Rexburg eclipse. I picked this one because most of the images you see of eclipses are highly processed. This actually kind of looks like something you'd see with your eye. We were there, we saw it. So you see the corona like this. You can see the little pink prominences, the hydrogen alpha emission, with your naked eye during totality. And really, you notice even in this picture, compare the blackness of the moon to the blackness of the sky, even away out towards the edge of the picture. There's always some sunlight floating around, some corona light maybe. You've never seen anything as pitch black in your life, and never will, as the moon in front of the sun during a solar eclipse. Now, if you photograph it, you can actually bring that out, and a lot of highly processed pictures do, so that you can see the moon as if this side were lit up. But you don't see anything like that with your eye. What you see is this, a real black hole in the sky. Those black holes that, you know, after supernovas, those general relativistic black holes Kip Thorne wrote about, those aren't real black holes. This is a real black hole. It's just a black hole punched in the sky. And another reason for being interested in eclipses is when I say they're cool, I don't just mean they're cool, I mean they're really cool. And David, while he was doing the photographs, recorded the temperature for us.
Actually, that was done by others, and I took a picture of it.
Okay.
I was way too busy and too lazy to do that.
Okay, so Lazy Dave took a picture of somebody else's list of temperatures. So whoever it was, there's no name on it. So whoever out there copied these temperatures down during the Rexburg eclipse, thank you, if you ever see this video. You can see that from pre-eclipse to totality, the temperature dropped 18 degrees, from 79 degrees to 61 degrees. We had to have sweaters. We brought sweaters with us. It was mid-August in Idaho, and we needed those sweaters because it was cold in totality. So it's not just cool, it's cool in a very physically real sense. And so most people did not see totality, they saw partiality. And so here's a picture of a partial solar eclipse. It's a white light image, but there's a filter on it that makes it look orangey. But you don't see sunspots like that on an H-alpha image. And this is something like what you'd see around here, partial eclipse. I picked this one because it's got a nice sunspot group in it. And we got a lot of nice sunspots floating around now because it's near solar maximum. Another kind of eclipse you get is this annular eclipse. You notice up on top here, I put the range of angular diameters for the sun and the moon. Our distance from the sun does not vary much. So its apparent size only changes by plus or minus 1 arc minute. But for the moon, you can see it's plus or minus like 5 arc minutes. So the moon has a considerable variation in its size. And if it's only 29 arc minutes across, because it's eclipsing the sun at apogee, it's going to have a smaller angular diameter of the sun, and this is what you're going to get. You're going to get a ring of fire because the moon is just too small to block out the sun. Now, the solar eclipses will go on for about the next 500 million years, because remember, the moon is moving away from the Earth. And in about 500 million years, the moon will be so far from the Earth, there will be no more total eclipses, only annular eclipses, because the moon will never be big enough to block out the sun. So we only have 500 million years left. You've got to catch your total eclipses now while you can, because they're going away, and you're not going to see any after 500 million years. Right? So the moon gets in the way of the sun as seen from the Earth. Sometimes the Earth gets in the way of the sun as seen from the moon. But remember from that earlier video, the Earth has a big, fat, long shadow. So the moon can be completely hidden in the Earth's shadow, which will never happen to the Earth in the moon's shadow. Once again, the geometry is exaggerated for educational effect. No, the sun is not that close to the Earth, and you should be happy about that. So here, as a matter of fact, tomorrow night, there is a penumbral lunar eclipse. It's September 18th, which is Wednesday UTC, but that's tomorrow evening, our time. So mid-eclipse is 7:44 p.m. tomorrow. The eclipse begins, let's see, the moon rises at 6:55 p.m. and the partial eclipse begins at 7:12. So it's not going through the whole moon. Only a fragment of the moon that you can see orange here is actually going through the umbra of the shadow. So it's not a spectacular eclipse. And Griffith Observatory is apparently doing nothing, because I looked at their webpage and there's no event going on here for the eclipse because it's really boring. It's a penumbral eclipse. But you might be able to see a little bit of the moon in red. I actually put the timings on here for Garvey. It's Tuesday. We won't normally have Garvey open. And I think the eclipse will be hidden behind the hill to the east of Garvey, so it's kind of useless to go there looking for the eclipse, because by the time the moon gets over the hill, it won't be visible. So it's not going to be a really exciting eclipse, but there will be indeed a penumbral and very little partial lunar eclipse tomorrow night. More interesting, perhaps, is a total eclipse like this one in 2022, where the moon actually goes through and completely engulfed in the umbra. So when you're near the edge of the shadow like this, and some edge of the moon will be brightly lit and the rest will be red. And when you're in the middle of the shadow like this, you're pretty close to the whole moon being really what you might call, or what they call, a blood moon. And so here is a photograph of the super blue blood moon over the Acropolis in Greece. It's a supermoon because it's at perigee. It's a blood moon because it's being eclipsed. And it's a blue moon because on January 31st it was the second full moon of the month. But it's blue and blood. So does that mean that this is an eclipse only for the upper echelons of society and the rest of us aren't supposed to look? I don't know. And so the moon actually looks like this. It has this copper tone reddish color. But as I said, if the moon is not completely in the umbra, you expect something different. And that leads us to an interesting project taken on by Brian May, the rock star of astronomy, and Jamie Cooper. What you see here is two images of the moon, totally eclipsed, except the moon at this point is not fully in the umbra of the shadow, so you notice that the upper end of the moon is lit up and not dark red like the bottom. But this is two images taken 8 years apart. This is not two images of the same eclipse. The phases of the moon repeat within an 8-year period because of the precession of the moon's orbit, I think. There's a bunch of periods involved that make it unclear what this comes from. And every source I looked at, they explain the Saros cycle, they explain the Metonic cycle. Nobody wants to try to explain this cycle. So I don't really know why. But the phases of the moon repeat every 8 years. And so what Brian and Jamie did was they photographed the moon, and then 8 years later they photographed it, same type of eclipse, only the orientation of the moon is slightly different. You know, the Earth is spinning, the moon is spinning, so the orientation is just a little bit different. And then they combined them to make a stereoscopic image, a 3D image, as if they had done that by peeking around the moon during one of the eclipses. So you can get your stereoscopic viewer, look at these two images, and combine them as if they are one 3D image of the moon. So if imagers out there want to take on a long-term project, here's something that you can go for. And in fact, I quoted Brian May here. As you can see, it took me and Jamie Cooper 8 years and some patience to make this 3D image, a compilation of two total eclipse moments some years apart, with the moon at slightly different orientations, giving us the headline to make a stereo image. Now the moon also gets in the way of other things, and then here's a grazing impact of Saturn in 2007. And in fact, the moon will do the same thing in about 8 hours, 7 or 8 hours from now, tonight, in the wee hours of tomorrow morning. The moon will occult Saturn. Not a grazing occultation like this. It'll last about an hour. The moon, Saturn disappears behind the moon at about 4:10 in the morning, this coming morning. and gone for about an hour. It disappears at a position angle of 75 degrees, reappears at a position angle of 216 degrees, and the moon will be in the far west. The moon sets at 6:02, sun rises at 6:39. So we should be able to see one if there isn't a marine layer. And that's the problem with being down here in the basin. So if you want to record or observe the moon blinking out Saturn, you got to get up above the marine layer, probably go up into the mountains or so in the wee hours of tomorrow morning. Or maybe as a star member, go to Scass, go to Lockwood Valley, and you should be able to see it from there. It won't be warm, but then you're astronomers and you're supposed to be used to that kind of thing. And sometimes stuff gets in the way of the moon. Airplanes, birds, and the International Space Station, which you see down here. And this is 1/2 second total exposure time from 1/2000th of a second per exposure, rapid fire exposures or a video. So you can see the space station crossing in front of the moon. Anonymous bird picture and of course your favorite airplane. And that's a very thin crescent moon. And there are some people, Norm especially, loves to go out hunting for moons right after a new moon, very thin crescents. And Leonardo da Vinci was the first person I know of to suggest that the reason you could see the moon like this as a thin crescent was earthshine. So the Earth, full Earth, seen from the moon, is almost minus 18 magnitudes, about minus 17.7. Different sources give you different numbers. It's about that. Which makes it over 100 times brighter than the full moon seen from the Earth. And you already know how bright a full moon is. You can read by it, it casts shadows. And so the full Earth seen from the moon is a real deal. It's lit up. Probably you could work in it just like daylight. It's bright enough. And the plot, because I originally made this talk years and years ago for an artist who wanted to talk about the moon in light. And so the plot shows you phase angle. A full moon is up here with an apparent magnitude around minus 12.4, something like that, 12.2. And a new moon down here at 0 has nothing. And so the moon, you can get the total brightness of the moon just by looking at the phase angle. And that is my inspiring talk on the moon, which I hope is acceptable. That's the end of the road, and I'll take questions from whoever wants to ask any.
When is the next total solar eclipse going to be visible from California?
I don't know from California. That's going to be a long time. The next total solar eclipse visible in the U.S., I think, is 2040. It's 45, is it? Yeah. Yeah, 2045. And there's two, as I recall. There's another one. Is that one of them just dips through the Dakotas, and the other one goes across the country again. And I can't remember which is which, but that's in the 2040s. They're close together.
What about lunar eclipse?
Oh, lunar eclipses happen all the time. I don't know when the next lunar eclipse is going to be, but it was a partial eclipse. There is a partial, well, the one that's happening, what was it, tomorrow or the 18th?
There is one in March, I believe.
Yeah. Yeah, this one is penumbral. And yes, I guess somebody says there's another one coming up in March next year. If it's well timed, then maybe Griffith will do something. They usually do if it's during the day, and sometimes they've dragged us out here at 2 o'clock in the morning, you know, for total lunar eclipses. But I don't know if that will happen again.
Thank you.
Hang on a minute. You're supposed to talk to the microphone. Let me unmute it. Are we unmuted? We are. Okay.
Hi.
Hi.
Thanks for that. Can you talk a little bit about the tidal forces and how they changed if the moon is closer or further away from the Earth? Thank you.
Okay. Can I talk about the tidal forces? Well, of course, I can actually talk about anything you can think of, but yes, and I'll make you all dizzy by flashing through my slides again. There we go. So, this slide, this slide shows you the mechanics of what's happening. The moon, what happened in my slides?
We're back.
Oh boy. Excuse me. The tidal force is a result of the fact that the moon and the Earth are not point sources. So here, you see like this point right here is being pulled on by this part of the moon and this part of the moon. But since they're in different parts of the sky, they're pulling in different directions. So they tend to stretch or squeeze whatever they're pulling on. And that's why the Earth gets a little bit squished. The simple argument is that the moon is pulling the water away from the Earth. It's a little more complicated than that because the fact that the moon is not a point source means that if you're the Earth, there is a downward component to the vector on the North Pole and an upward component to the vector on the South Pole, and that means there's a net force that actually squeezes the Earth. So you're used to the ocean tides. That's what makes high tide and low tide at the beach. The Earth itself also has ground tides. The Earth deforms, but its deformation is much smaller than that of the water. It depends very much on the distance. So when the moon formed, it was probably only about half its current distance from the Earth, maybe closer. The Earth spun around much faster, so the length of day after the moon formed was probably 12 hours instead of 24, something like that. The Earth was moving a lot faster. And the moon was moving away a lot faster, because as the farther away the moon gets from the Earth, the slower it moves away from the Earth. But right now it's moving away from the Earth anomalously fast because of plate tectonics. The north-south arrangement of the continents of North America and South America block the oceans, practically from the South Pole to the North Pole. There's no place for the oceans to go. We dug the Panama Canal, and the ocean doesn't do that. And so the tidal bulge of the oceans hits those continents and transfers momentum to them and transfers momentum to the moon. If you break up that continent and let the water go through, then you get less efficient transfer of angular momentum from the oceans to the moon, and the moon does not move away as fast. Does that help answer your question?
Yes, thanks, Tim. But also, does the tide change like when the moon is further away in its cycle?
Does the tide change when the moon is further away in its cycle? Not appreciably. Of more importance is that there is a solar tide, which is smaller than the lunar tide, but not insignificant. So when the solar tide and the lunar tide combine, now you get an extra high tide, which I think is what a spring tide is. And then when they cancel each other out, it's a neap tide. And so you can get an extra special high tide when the solar tides and the lunar tides line up. Every object in the solar system exerts a gravitational force on us, but they're far away. Even Jupiter's far enough away that you really don't need to worry about tidal forces. It's just the gravity of Jupiter, which is roughly the same in magnitude. Yes, I'm going to get into real trouble now, but if a baby is being born, the gravitational force of the point source doctor is roughly the same as the gravitational force of Jupiter. But the tidal forces are much larger because the doctor surrounds the baby and Jupiter doesn't. Therefore, if you want to do astrology correctly, you have to account for the doctor who's in the room. and the nurses and the pillows. You get the idea. Yeah.
Tim.
It's muted at the moment.
I'm a boater, and I one time asked someone for a tidal clock, and they sent me one, and on the West Coast, it was never right. I had set it, and it would quickly drift off. But I understand on the East Coast, it's accurate. Have you heard of that?
I haven't heard of that, but the tidal wave, as you can see from this diagram, the Earth is turning under the oceans. This configuration of the oceans is basically fixed with respect to the moon, and the Earth is turning under it. So there is a friction at the bottom of the oceans between the ocean and the Earth. And so the tides are going to arrive at a different time at different parts of the Earth, because the Earth it's the rotation of the Earth that sets that. So you probably need to just reset it to West Coast tides and it'll work. That's my guess.
Up there? Okay.
Any questions out there in Zoom land?
Hey, Tim. I was just curious if you knew much about some of the economic interests people are having in going back to the moon. Like, it seems like there's a lot of natural resources like water, and I've read something about helium-3 up there. I wasn't sure if you knew anything about that.
I'm not altogether sure how much helium-3 there is on the moon, but I'm sure you could find it in the solar wind. There certainly is a lot of mineralogy on the moon. Like I said, the creep terrain has potassium, rare earths, which you need for batteries and computer chip applications, right? And phosphorus. And remember that the moon is made out of basically the same stuff the Earth's mantle is. So the mineralogy of the moon overall is not going to be terribly different from that of the mantle. So there are undoubtedly valuable resources there. And I would think that from an economic standpoint, digging them up on the moon and then dropping them back to the Earth is a lot cheaper than digging them up on the Earth and launching them to the moon. Now that might be wrong there, but it seems to me that mining the moon and sending your results back to Earth would be cheaper than sending stuff from the Earth to the moon. For really rare elements, you have to be a little bit careful, because like gold, for instance, or something that's particularly valuable, if you suddenly found a huge deposit of moon gold and shipped it all to the Earth, well, then the market price of gold would collapse, right? Because we now have umpteen zillion more gold tons to sell. So you have to be a little careful. I think the primary interest is in going to the moon to establish industry on the moon, so that instead of launching things into space from the Earth, you launch them into space from the moon, which has a lot less gravity, which means that big rocket that I was talking about before can be a lot less big because you're launching off of the moon, and you save a lot of money that way. Greg?
Do the tidal forces play? Do the tidal forces between the tidal forces that affect there, does that play any role in plate tectonic itself?
I don't think the tidal forces play a role in plate tectonics, but they could, because remember they're solid earth tides. They could have an effect on earthquake faults that are ready to go. So you might be able to trigger an earthquake by that last straw that breaks the legendary camel's back. And I don't know what people have against camels, but anyway, that force might trigger a cascade of events that then starts an earthquake. Geologists seismologists have looked into that, and if it's a real effect, it's not very big. There's no real noticeable thing there. As plate tectonics is primarily internal, And the primary driving force is what's called slab pull. So when you have subduction, it's like a siphon. The part of the plate that's being pulled down pulls the rest of the continents with it. And so you get seafloor spreading in the mid-Atlantic and that kind of thing. And those internal forces are dominant.
Spencer, any from the Zoom? Or Alicia? Anybody there? See if there's something in the chat.
Let's see. There's just one comment on the simulation. I've seen that simulation before. I've been curious if that was one of a bunch of educated guesses that happened to produce a plausible moon-forming result. Or do we know enough to reproduce that simulation reliably?
I would be very surprised if that was the only simulation they ran. When you do this kind of thing, yes, you run a whole bunch of simulations. Anybody who simulates anything like that's going to do. Never going to just run one simulation and say, okay, I quit because it didn't work. Or run one and say, oh, wow, I'm a genius. It works great. You run a whole bunch. And the point is you're looking for something that will solve your problem in a plausible way. And so, as I said before, one of the problems is too much angular momentum in the system. The moon is made out of the same stuff as the Earth's mantle. The Earth is anomalously hot. Why isn't the Earth cold like everything else? The Earth is too hot. So you have these problems and you're looking for a way to solve them. And if you can find a way that solves all of them at once, then you feel really good about yourself. And that undoubtedly is the simulation that was the most efficient at solving those problems, but remaining a physically reasonable thing. So if you look at the grazing, low velocity impact, it does the kind of thing you would expect to happen. There's nothing going on there that's really weird. And so it's not supposed to be an exact reproduction of this is exactly what happened, but this is the kind of thing that happened. Maybe the angle was different, maybe the original collision was different in details, maybe there were 3 blobs instead of 2, but you can still do the same thing. You can sling the moon up with a gravitational slingshot from the other big blob that falls in. All that works and makes sense. And so what we're doing is representing the event rather than try to reproduce the precise and exact details of the event, because that's kind of impossible without being there to watch it. And it didn't look like the kind of place you'd want to be hanging out close to. You know, you want to stand away from something like that. Anything else? Are we done? We're done. Oh boy, we're done. Thank you.
Okay,
Thank you, Jim.
I posted the link for the raffle for those guys on Zoom. And there are only 10 people who signed up for the raffle so far on the Zoom.
Okay, Alicia, are you there?
Yes, I'm here.
Okay, we only have one laser here at Griffith, just so you know. So we're going to need to take the names and emails and numbers for the raffle.
Okay, that's good to know. Thank you. I will adjust accordingly.
Okay, we ready to go, Tim and Daryl, for the raffle?
Who's going to do
or anything else you need to say?
Alicia was going to do the raffle.
Oh, okay. Well, I got we go back and forth.
From inside the Zoom, she can do the whole thing. You can do it. So I can get one of
Alicia has to tell us what we're winning.
Okay, for those of you on Zoom, I'm going to close out the raffle in another 30 seconds. So go ahead and register if you want to be on the raffle.
While we're here, I just want to let the people know that Dr. Fields is here from Pierce College. He's one of our new members, right up here. And he runs an amazing planetarium show at Pierce College. It will be October 14th at 5 o'clock, and he has a seating capacity of 50 people. And if you haven't seen one of the shows, definitely worth seeing. Okay, should we start over here, Alicia?
Okay, let's do
Okay, here we go. All right.
I should turn off my microphone.
How many tickets are we giving away tonight here at Griffith?
4.
4. Okay, here's number 1. Your ticket's out, 833. I'll do this in my announcing voice. 833-5038. 5038. Congratulations. There you go. You did tonight. Okay, so we need to get your name and number. So how do you want to do this, Tim? Want me to do the next one? I can do them all real quickly here, and then you can continue the rest with you, Alicia, okay?
Okay.
Okay, here's number 2 for Griffith. 833-5033. Right over there. Come on down and... And well, what did they win, by the way? What's the first one?
All right. So
I have a laser here. I have one laser here.
Yeah, the first person won the Observer Sky Atlas book. The second person won Constellation Glasses. And the next person will win a laser.
Okay. And what is your name, the guys that won, so we know?
Alan.
Alan what?
Alan Durr.
Alan Durr won, and?
Mark Salzman.
Mark Salzman, our winners. Give them a hand, yay!
Make sure you write down what they want.
And what they won, you write it down, yeah. Okay, next one. This will be number 3. 833-5035. 5035. No.
They want to
Try it again. 833-5035. Anybody? Last call. Okay, we'll try a different one. 833-5029. Here we go. Come on down. And what did this gentleman win? The third person?
A laser.
Okay, I'll give him the laser from here then. Okay, so we can mark that. We have that he has the laser. And your name?
My name is Sarah Kolesnikov.
Welcome. Congratulations. Thank you. Big hand. Come on, guys. Woohoo! Okay, so that's 1, 2, 3, and one more. Last one here at Griffith will be 833-5031. Greg? Okay, Greg Thomas. What did Greg win?
He won Celestron Skymaster 15x70 binoculars.
He goes, yeah. Okay, we are done here at Griffith, so thank you. It's all yours, Alicia.
Okay.
Okay, so for Zoom, let's see. First one is Elizabeth Wong.
Okay. She won a LAS Online Star item.
Okay, let's see. Yep. Shane Winter.
He won a map of the moon.
Okay. Debbie Balassi.
How do I spell her last name?
Valise.
Yeah. And she won an eclipse book.
Okay.
Yeah.
And one more.
Yeah.
Christina Cabero Mino.
She won a hot and cold Keurig.
All right, was that it?
Yep, that's it.
Okay.
Thank you. Okay,
All right.
that wraps it up.
Okay, I think.
Oh, where did it go? Oh, well. We didn't record the prizes that the first two won, so can you repeat what those two were for us?
Sure. So the first two were the Observer Sky Atlas book, and the second was Constellation whiskey glasses.
Okay, thanks.
All right, and for Christina, who posted in the chat how we pick up our raffle items.
Constellation.
So Christina, Alicia has your email information, so she'll get in contact with you.
Mhm. Yeah. And I'll also check to see if the winners have won these items beforehand. I might switch it up to give them something they haven't won before. So, but we'll stick with this for now.
Alicia,
Yes?
Greg has a question for you.
What's up?
Alicia, could you give an update on the astrophotography contest? I don't know if it's going now or it's coming up, but I know we were talking about it.
Yeah, so the astrophotography contest is open. I know we were starting later in September, but I figured since we already sent out the link, you're more than welcome to submit your images. People have already started emailing me with questions about the categories and the rights for the images. So feel free to submit, and there will be a total of 12 winners who will win a night at a half night at the Mount Wilson Observatory. So, is there anything in particular you wanted to know about, Greg?
I'll talk to Alicia later.
He says he'll talk to you later.
Oh, okay.
Here.
Yeah.
Alicia, are we giving away those half nights for all the photography winners? Is that right?
Oh, we're giving them to the winners, not the runner-ups.
Okay.
The next general meeting will be the third Monday in October instead of the second Monday because of Columbus Day. And our speaker will be Konstantin Batigan, from Caltech, who will talk about his search for Planet 9 or Planet 10, depending on your opinion of Pluto. Thank you.
10.
I think, is that it? And then we're all done, or? That's it. Say goodnight to everybody here.
All right.
All right, everyone, that's
night,
it
Dan.
for the meeting for tonight. Thank you very much for coming. And thank you, everyone that showed up on Zoom as well. We had a nice showing on Zoom tonight.